Welcome to section 3.3, common log, natural log, and change of base formula. Today we're going to start using our calculators a little bit more as we continue on with logarithms. A couple things, we're going to evaluate common logs. We'll talk about what common logs represent, and then we're going to talk about natural logs as well. And then we're going to do the change of base formula, which is going to be important in terms of plugging things into our calculator correctly when the bases are not base 10, which is the common base. So to kind of jump right into that, the common base for logarithms is base 10, all right? And so when you see a logarithm that doesn't have a number written there, it represents base 10. So you have log base 10 of x is equal to log of x. So if you don't have a base there, it does represent log base 10. That's what's built into the calculators, all right? So all of this stuff that you press when you press log, it's base 10 when you plug it in. So if you have something that's base 2, we're going to have to talk about how to accomplish that when it's a different base than base 10. So that's the common logarithm. That's the most common base that we have, that we use. Now, the other one, and that is used just as much almost, is called the natural logarithm. Now, this is still a logarithm. I think a lot of people get confused that a natural log is not a logarithm. It's something different than a logarithm in terms of what we've done in the past. The second most common base is what we call base e. Base e is an irrational number, just like pi, and the way it's calculated is, this mess of things. And I know you're looking at this like, what in the world? You don't necessarily need to write this down, but this is where it's calculated. It's from a summation. It has to do with this factorial. And so what happens is if you add this, because it does go to infinity, if you add this over and over and over again, we get closer to this value 2.7183, and as I said, it continues on. So that's what the value of e represents. And if you want to figure that out on your calculator, if you look at the log button, right below that is ln, and then on your second key, if you press second, it does e. So if you do e to the first power, that's where that number is. So if you ever need to find that on your calculator, that's where it's located. And so that value is, like I said, 2.7183 approximately. And so as we look at this, what does natural log? Well, on your calculator it says ln, but what does this mean? So, well, if I have e raised to the x power is equal to y, let's rewrite that as a logarithm. So we have base e, so it's log base e of the y value is equal to the exponent. A logarithm is an exponent, so it's equal to the exponent of x. Well, log base e can be rewritten and will be rewritten as natural log. Okay, those two things are equivalent. Natural log does not have, you're not ever going to see a base on a natural log. So you'll never see natural log base 2, natural log base 10. You're never going to see that because the natural log is only base e. And so when we write natural log of 3, another way to think about this is log base e of 3. And the base e on our calculator is natural log. So natural log of 3. So we'll kind of talk about more about that, but all of the properties that hold true for logarithms hold true for natural logs. They're both logarithms. Common log is base 10, natural log is base e. So let's take a look at a couple problems here. This is kind of how I originally started the whole exponential unit / logarithm unit. Is we started off with a problem like this, and we said, okay, how do we solve this? 3 raised to what power is 5.1? Well, we can approximate it, but we don't know what it is exactly until we get into logarithms. So the other day I was showing you how if you have log base 3 of something and you want to get rid of the logarithm, so to speak, you have to use its inverse. And you would say 3 raised to log base 3 and 3 raised to the second power. So this would cancel and you'd be left with x equals 3 squared, which is 9. Well, when they're in exponential form, it works the same way. But to undo those, you're going to use logarithms. So since the base is 3, we're going to rewrite each side as log base 3, and now we're going to rewrite that as 3 to the x. So 3 raised to the x is right here. I chose base 3 so that the bases would cancel, and then on the other side we have log base 3 of 5.1. Now what happens on this other side right here when you're going to do this? Well, log base 3 of 3 cancels and you're left with x, and x is equal to log base 3 of 5.1. Now that's the exact value. How do we approximate that? I'm going to get back to this question because right now we don't have base 3 on our calculators. All right, we have logarithms, which are base 10. All right, and we have natural logs, which are base e. So we don't have base 2, 3, and so on. So we'll come back to that in just a minute. Same thing on b. You know, it's base 4. So you could rewrite this as log base 4 of 4 raised to the x. And then you have to do the same thing on the other side. Log base 4 of 7. The reason we choose base 4 is because the base of the exponential is 4. It cancels out, and you're left with x equals log base 4 of 7. Once again, we don't know what that is, so we are going to have to get back to this question in just a little bit. So to get back to this question, we're going to move on to something called the change of base formula. So what happens on your change of base? Well, I have a logarithm, log base a of x is equal to y. And what we want to do is we want to try to figure out a different way to write this. So we're going to start by rewriting it exponentially. So log base a of x is equal to y. We're going to rewrite this exponentially. So a raised to the y, which is the exponent, a logarithm is an exponent, is equal to x. Now that it's an exponential form, we're going to, just like I did a second ago, you know, we chose a certain base on these, base 3 and 4, but because we're doing a general form, you know, we don't know what we have here, so we're going to choose any base that we want. We're going to say, all right, well, this has to be equal to log base b of a raised to the y is equal to log base b of x. Alright, and then the y, which is an exponent, can get moved to the front. So you have y times log base b of a is equal to log base b of x. And now we solve for y by dividing by log base b of a. And so what do we get? We got y is equal to log base b of a divided by log base b, oops, I wrote the wrong thing, log base b of, I'll start over. So y is equal to log base b of x divided by log base b of a. And so what was y equal to from the beginning? This. And now it's equivalent to this. So the change of base formula, I'll write it out, would be anything that's written as log base a of x could be rewritten as log base b of x divided by log base b of a. And the b just has to be some number that is greater than 0 and cannot equal 1, for the same reason that we had earlier. Alright, so that's what we have in terms of the change of base formula. So this right here means we can change the base of any logarithm. So when we go to evaluate this problem down here, log base 4 of 25, well, we can now rewrite this as, okay, we don't have base 4 on our calculator, but we can choose any base we want. We can do log base, I'll write it this time, log base 10 of 25. I don't know what's going on with my 2's here. Log base 10 of 25 divided by log base 10 of 4. And since I chose base 10, then we can go to our calculator and we can say, alright, we're going to do log, which is base 10, so we'll do log of 25, close the parenthesis, divided by log of 4. And now that we divide those, we get approximately 2.3219. And we're going to round these to the nearest thousands. So tens, hundreds, thousands. So let's go back here and we approximate that to be 2.321, I forget, 2.32, oh, I just lost it. Oh, there it is, 2.3219. And there we go. And so even though we don't have base 4 in our calculator, we can rewrite it as base 10. We could also use the second most common logarithm, which is base e. and we could do the natural log of 25 over the natural log of 4, and watch what we get. So let's get that one back up there so we can see it, and then we're going to do the natural log of 25 divided by the natural log of 4, and you can see it's exactly the same thing. It doesn't matter what base you use when you go to evaluate this. So you can do base 10, your common logarithm, you can do base e, your natural logarithm. Let's go back to those two problems that we got kind of stuck on. So now that we know the change of base formula, log base 3 of 5.1, now we can do that. We can say, all right, well, x is equal to log of 5.1 divided by log of 3. And then you plug that in your calculator, and we get a value of approximately 1.483. So 3 places, round to the nearest thousandth. And go back over to B here, and you have, I just realized these parentheses were in the wrong spot. There you go. Now we can rewrite this as x equals, let's do natural log on this one. So we'll do x equals natural log of 7 divided by natural log of 4. Because remember, it doesn't matter which base we pick. And then when we plug that into our calculators, we get x to approximately be 1.404. And there you go. So now you guys can evaluate logarithms with different bases besides base 10 and base e. So the last thing I'm going to finish up with is we're going to do some applications, some compounding interest problems. But really these are going to be ones that you're just going to be able to plug into your calculator. You just got to make sure you have the right numbers in the correct place in terms of the formula. And then later on this week into next week, we'll start looking at some more complex problems. So let's just take a look at these. We've got compounded continuously. A is equal to PE raised to the RT. So you see that irrational value of E in there. So that's why we're going to get back to logarithms eventually a little bit later. And then on the other one, compounded any other time. So A is equal to P times the quantity 1 plus R over N raised to the NT. And here are your values as to what things are. A represents the account balance. P is your original or your principal amount. R is the APR. That's your rate in decimal. Make sure it's in decimal. T is the time in years. And N is the number of times compounded per year. So it's the number of times that you're compounding it per year. Alright, so let's go ahead and take a look at our last example. I've given you one problem, but I'm asking you to do 2 different things. Calculate the balance for each account if the original investment is $2,000. On A, I want you to do it continuously for 5 years, and on B, I want you to do it quarterly for 5 years and kind of compare them and see what the differences are. So we're doing 4.2%. Alright, so the first one that we're going to be using is, since it's compounded continuously, we're looking at A equals P E raised to the RT, and we're going to plug in what these values are. So 5 years represents the time. Here's your rate. Does need to be in a decimal form though, so that would be 0.042% out of 100. And we know that the investment, alright, the original investment, that's your principal or your original amount. So we're trying to find the new amount. So A is equal to 2,000 times E raised to the RT. So R is 0.042 times T of 5 years. And really at that point, once you have those values in, you're just going to plug that into the calculator. So we say 2,000. E is the second function of natural log. It's the inverse. So it's E raised to, and I got 0.042. Don't close the parentheses, just press times 5, because if you close it, then it's not going to do it in the order. You want to raise it to those values being multiplied together. And so I got $2,467.36. So A, make sure we label, we got the dollar amount here, $2,467, and we'll round up to 36 cents. And so that's compounded continuously over 5 years. Now let's switch directions a little bit, and we're going to do quarterly. So we still have the rate, we still have the time, We still have the principal up there, but quarterly, how many times does something happen quarterly? Well, that's 4 times a year in this case. So we'll use our other equation where it's compounded at at any time, this one quarterly, so we'll use that one. So A is equal to P times the quantity 1 plus R divided by N raised to the NT. So let's plug in the values that we know. The principal, once again, the original amount is 2,000. 1 plus the rate, 0.042 divided by 4, that's quarterly, raised to the 4 times 5. And once again, we'll take that and we'll plug it into the calculator and see what we get. So we have 2,000, 1 plus 0.042, divide that by the quarterly, and then we're going to raise it to, and if you know, once again, if you type this in, you're going to have to use parentheses 4 times 5, but we know 4 times 5 is 20, so we'll just type in 20 here, and we get close to what we had before, $2,464.66 if we round up. So this answer is A equals $2,464.66. So if we do it continuously, we make a little bit more money over 5 years. Now as this goes on, 10, 20, 30, 40 years, it's obviously going to be a lot more as we go on, but not a big difference as of right now. So those are ones that you're just going to be plugging into the calculator. Make sure you get the numbers in the correct spot. And here's your homework. It's going to look like a lot, but there's a lot of different things going on here. A lot of things that you're just plugging in. So take a look at that. We'll work on that tomorrow in class. Thank you.